Hello, welcome to Pipeline Integrity, Gamma Exponent Model Validation Part 4. My name is Colin Scott. I'm a pipeline integrity engineer based out of Calgary, Alberta, up north in Canada. Today's topic is going to be validation of my Gamma Exponent model, and today I'm going to be looking at circumferential cracks. Some of you might have seen some of my previous videos where I looked at axial surface breaking cracks or looked at corrosion metal loss. Today I'm going to be looking at circumferential cracks. They are a slightly different beast from the axial version, simply because the tests that are done to validate are typically done in bending rather than in tension. So there are a couple of things that we need to think about there and come up with a correction factor to account for that bending stress. So those of you that are watching the video series might be familiar with my Gamma Exponent model here. You'll see that it's mathematically in a very similar form to the original log secant model that was put out in the 1970s by the NG18 committee at the Battelle Institute in Columbus, Ohio. The key thing with this GEM model, though, is that it's been mathematically derived based on depth of a surface crack, as opposed to the original log secant model was originally derived based on length for through-wall cracks. So there are a couple of fundamental differences that I've put into hopefully improved model agreement to actual real burst pressure data. So starting from the left, we have a remaining strength, and that's going to be the predicted failure strength over the flow strength. Then we have 1 minus A over T, which is the remaining ligament, all of that to the power of the gamma exponent. There's a 2 pi factor in there, arc cosine exponential. The K squared is our material toughness. We have a 10 factor to think about. A is our crack depth, and then the flow strength there squared as well. In the case of a surface breaking crack, the gamma exponent is defined as the minimum of the crack length divided by the radius of the pipe up to a maximum of 1. It's important that we look at that gamma exponent going up to 1. When we do some work with the metal loss and corrosion, there's actually a limit of 1/2, which makes quite a bit of a difference. Here we're going to go to a maximum of 1. So there's quite a bit of fine print for the model. Nothing too serious that will inconvenience anybody too much. The model was essentially derived from a flat plate solution, so because of that we really have to specify it should only be used on thin wall pipe. I've come up with a somewhat arbitrary D over T value of greater than 20. The flow strength that I'm using for all the validation work is yield strength plus 69 megapascals or 10 KSI. That's pretty standard. I didn't play around with any of the other flow strength definitions. That might change the numbers a little bit, but so far the current yield strength plus 69 seems to be working fairly well. I can adjust my flaw depth by a pi over 4 factor if I need to work with semi-elliptical profiles. For the metal loss and corrosion work, I've come up with what I call my level 2 ELM algorithm. It's a little bit like R-Strang, but a little bit different too. And that can be used if you've got a full flaw profile available. Now I'll say that the level 2 ELM algorithm, I haven't actually been able to validate that on any crack profiles. It's only been validated on metal loss. So that's kind of a work in progress. If I'm doing stress corrosion cracking work, well, specifically axial stress corrosion cracking work, I modify by a 0.63 factor or a 0.84 factor to account for stress corrosion crack shielding effects. If you've seen video number 2 in this series, I've actually done the validation to a bunch of data that demonstrates that there actually is a difference for the hydro tests and the service factors there. So please take a look at that if you're interested. I will be working on a separate video that demonstrates where I got those 2 numbers from. I did not pull them out of thin air and they seem to work. There actually is a technical rationale based on some classic stress intensity factor solutions. More fine print, as I mentioned, when you use the gamma exponent for a metal loss or localized corrosion, there's a limit of 1/2. The limit for all of my other flaws is 1. The toughness used for validation is the lower bound Wall and Sharpie correlation that you can find in API 579. Or you can use the J equals M delta yield strength if you happen to have some CTOD data. And with that, use an M factor of 2 for plane strain conditions. Now I need to specify here that the Sharpie over area, that toughness correlation that some people would use typically, is not recommended for this. I have, I think, a pretty good technical rationale on why that should not be done. I won't explain it here, but if you go to my other video series, which is called Pipeline Integrity, things that make me go, take a look at video 4. That explains why the Sharpie over area is really not recommended for most of the conditions that we're working with. As I mentioned at the intro, circumferential flaws typically are tested under bending conditions, and so we require a bending correction factor, which is not required for the axial flaws. And I'll say flat out that this bending correction factor is a work in progress, and I'll explain to you why. There are a few if, ands, or buts associated with the data, and so I really need to just basically write this bending correction factor in pencil rather than pen until I get some of these data issues figured out. And until further notice, I don't recommend using GEM for cold welds or grooving corrosion. I've been having some trouble on finding appropriate data to validate the model. Now here's where things get a little bit tricky. I did find some industry failure data. One set of numbers came from Choi, a doctoral thesis from the University of Waterloo back in 1997. And Choi referenced two papers that I am not really able to find. They're fairly old. They're from 1983. I'm not sure if they would even be available as electronic copies. They're probably buried under a pile of dust somewhere. But Choi referenced Glover and Coote, 1983, and then Glover, Coote, and Pick in 1981. So there's a good pile of information there, but my second set of industry failure data comes from Smith and Pizarski, and that's from a conference in 2009, and they were looking at comparisons of API 1104 and BS 7910 assessments for girth welds. Now, the paper that I found from Smith and Pizarski, they referenced Coote, Glover, Pick, and Burns 1986, which again is a different paper. They mentioned Glover, Coote, and Pick 1981, which is what we saw from Choi, and then Pick, Glover, and Coote from 1980, which is another different one. So what I decided to do was to compile my two sets of data, and I could not cross-reference these against these old 1980s papers. So what I decided to do is only use the data points in which I got consistent data sets from both Choi and Smith. That meant that I could only use about half of the data. In some cases, Choi had some data that Smith didn't. In some cases, Smith had some data that Choi didn't. And in some cases, there were a couple of differences in the number that made me a little bit suspicious of whether things had been transcribed correctly. So what I ended up with is 25 data points, but I can't give them my full blessing because I have not been able to cross-check them against these old 1980s papers that are probably lost in the history of time. So I hope you'll be okay with that and just bear with me. Now, in order to come up with a bending correction factor, what I did is I just did a basic GEM validation. And then I plotted the conservatism in each data point as a function of the crack depth ratio. And I found that the predictions actually became more and more conservative as the cracks got deeper. That might not make a lot of sense here intuitively. When you think about it though, if you have an external crack on the outside of a bend of a pipe, you're not going to get an even stress distribution along that crack. You're going to get a peak stress right in the middle of that crack, and then as you go to the outer lengths of the crack, you're actually going to be feeling less and less stress. And not only that, when you consider that you're actually under displacement controlled conditions as opposed to load controlled conditions, you're not going to get the full effect of the stress intensity factor working on that crack. And as the crack gets deeper and deeper, I think that those displacement controlled conditions play more and more of a role. I think things would get pretty complicated to come up with a real correction factor without doing a very detailed series of finite element analysis, which is beyond me. So what I did was I just looked at the conservatism I had as a function of flaw depth ratio. I put a trend line through the data, and through that reversed out a correction factor here. So what I've come up with is the strength of a flaw under bending is approximately equal to 1/2 times the crack depth ratio plus 1 times what the strength would be in tension. So essentially, use the gem as usual, and then multiply it by this factor. You'll find that there's actually a higher apparent strength when you're under bending. And it turns out to be, quite a fair factor there. So when we do that and we look at our various data, this is kind of the agreement that we get. It's not perfect, but quite frankly, it's not too bad either when you consider that I'm using a generic gamma exponent model which has been developed for axial flaws, and I've just sort of come up with an empirical fudge factor that corrects for bending. It's not too bad. Here I've got the y-axis, I've got the predicted failure strength using the gem with that correction factor. And then on the x-axis, I've got the true measured failure strength. So that's a failure strength that comes out of the papers that I found. When I put a trend line through there, I get y equals 0.96, which means that I'm a few percent overly conservative on average. Now, you'll see that there are a few data points above the line, and these represent non-conservative predictions, meaning that it's potentially unsafe. And then I've got some data points below the line, and these are overly conservative data points, which is good, but potentially expensive. And those data points tend to somewhat offset each other to get a pretty good prediction. Now, if I wanted to get really serious about this, I would probably also look at a way to put in a length correction factor. But the way the gem has been developing, I've been sticking with depth correction factors, and I'm going to stick with that for now because it seems to be doing a fairly reasonable job. When I look at the statistics, like I said, I'm doing this as a work in progress. When I use the basic gem equation with the bending correction factor that I just showed you, I get an accuracy which comes out at 1.03, meaning I'm just about 3% overly conservative. And when I say the accuracy, I'm basing that on mean of the failure ratios, where the failure ratio is defined as the true failure strength divided by the predicted failure strength. And then my precision comes out at 13%, and that's just simply a standard deviation of those failure ratios. So in the great scheme of things, I think that that's pretty positive. Obviously, people out there that have taken a good look at API 1104 or have done work with various other models like the next section collapse model and such used by the nuclear industry, will recognize that this is really not an easy game to play. And to come up with an accuracy of 1.03 and a precision of 0.13, I think in the great scheme of things is actually pretty good. Now, if you're interested in seeing some more videos, I do have another video series which is called Pipeline Integrity, Things That Make Me Go, and that's a 6-part series. That video series is a critique of the NG18 based assessments for both corrosion and cracking. And the reason for that is those original equations from the 1970s actually mathematically focused the failure pressure predictions on the flaw length. And that's really not appropriate for a surface crack. You really need to focus things on the flaw depth. I'd also like to point you towards the other 5 videos in this series. I'm doing validation on all sorts of flaw types. So today we looked at circumferential cracking, but if you watch some of the other videos, you'll learn about axial surface cracks, stress corrosion cracks, which have a crack shielding factor included in them. I look at corrosion metal loss, and then I also look at axial through-wall cracks for leak rupture boundary analysis. I think if you watch those videos, you'll find that this gem model seems to be validating quite well, not just here for the circumferential cracks, but for multiple flaw types. So please dig around and find those videos if you're interested. If you're less of a viewer and more of a reader, I do have 3 papers that are, official papers, peer-reviewed. For those of you that are mathematical nerds, I'd like to point you towards the 3rd paper there, which is my ASME Journal of Pressure Vessel Technology paper, and that's where I go through all the mathematics of how the model was derived. That one is a lot to chew on, so I only recommend that for people that are mathematical nerds like me and interested in theoretical stuff. If you've made it this far, thank you very much for your time. I hope you followed along with my logic and things kind of make sense. If you are interested in model validations, please take a look at the other videos. And until next time, thank you for your time.